Welcome to Lesson 12, and let's explore data types in Standard SQL and how Postgres implements them. We'll start by understanding what data types are and why they matter. Then we'll explore numeric data types, including integers in various decimal options. We'll move on to text data types and how PostgreSQL handles them when they get large. We'll also cover temporal types, discussing Unix timestamps and time zones. Finally, we'll look at other important data types like booleans, JSON, and wrap up with type conversions and casting. Let's begin with the basics. Data types define the kind of information that can be stored in a database column. They are not just labels. They shape how the database manages, stores, and processes your data. At the most fundamental level, all data in a computer is stored as bits, binary digits that can be either 0 or 1. In case you think binary digits are complicated, let me tell you one thing, they are much simpler than decimal integers, unless you are dealing with floating points. Miss Lovelace is a fluffy smart cat who needs to tell her human flatmates things like the number of biscuits or the minimum litter box size she demands. Because humans are much less evolved than cats, her mates gave her a set of monochromatic lamps to communicate with her. Sorry about them, as they knew nothing about colorful LED lamps. Miss Lovelace taught them that switched off lamps mean 0, while switched on ones mean 1. So how can she communicate that she will go out tonight at 9 p.m? Well, she needs more lamps. She brought up a second lamp to the left of the first one and determined that the first lamp off and second on means number 2, and she can still switch both lamps on to represent the number 3. She now has 4 different combinations, from 0 to 3. You can now imagine that with a third lamp, there will be twice as many combinations, right? Giving her 4 numbers with this lamp off, and the same 4 numbers with this on. In other words, Miss Lovelace can represent 8 numbers from 0 to 7. It's still not quite there yet, and you guessed, a 4th lamp doubles the number of combinations again, allowing her to express numbers from 0 to 15. Our cat-lamp thought experiment shows how binary works. Rather than having 10 possible numbers in one digit, 0 to 9, you can only use 2, 0 or 1. Rather than multiplying by 10 on every next digit, we can only multiply by 2 on every next digit. So now you know. These digits, or bits, are typically grouped into bytes, where each byte consists of 8 bits. Following this pattern, with 8 bits, 1 byte, we can represent 2 to the power of 8 as equals to 256 different values. This is why you often see references to numbers like 255 in computing. But what about negative numbers? Well, that took Miss Lovelace a bit more time to teach her friends. She said, no matter the number of lamps you give me, if the first one is on, the final number is negative. This way, half of the numbers are 0 or positive and half are negative. Positives start from all lamps switched off, which is 0, and go up as we switch them on. While the leftmost lamp is off, you know the number is still positive. When on the other pole, negatives start with all lamps on, which is -1, and go down as we switch them off. While the leftmost lamp is on, you know the number is still negative. Because of that, she now needs 5 lamps to get to the number 9 for 9 p.m. because 2 to the power of 5 is 32. Hence, it can represent numbers from -16 to +15. It's not +16 because of 0. Can you guess the combination of lamps she presented to her friends? Therefore, as 1 byte contains 8 bits, instead of going from 0 to +2 to the power of 8, it goes from -2 to the power of 7 to +2 to the power of 7 minus 1. To put in a formula, -2 to the power of n minus 1 to +2 to the power of n minus 1 minus 1, where n is the size of the data type. In this case, a byte. then it goes from negative 128 to positive 127. When it comes to storing text, we need to consider encodings of character sets. An encoding is a way of representing characters as numbers, which can be stored as bits and bytes. For example, one of the first and most popular character sets is ASCII, which uses only 1 byte, 8 bits, or 256 possible combinations. The uppercase letter A is represented by the number 65. The lowercase letter a is represented by the number 97. Unfortunately though, ASCII is too small and doesn't represent all humankind's invented characters. There are several other character sets, for example, the famous Latin one, also known as Western European, is standardized on ISO IEC 88591, and the base of other famous char sets like Windows 1252, extended the original ASCII table to 191 different characters, still below the 256 limit. The problem with these char sets is 8-bit representations, while storage efficient, cannot represent important characters from non-Western European alphabets. Yep, and also emojis. This is where Unicode comes in, providing the standard that aims to represent all writing systems. As the Unicode standard, maintained by the Unicode Consortium, is just an abstract agreement of what characters humans have ever invented, there are different encodings to represent the actual characters. Most of the time, encoding and char sets are synonyms. However, a very subtle difference is that a char set is exactly what the name suggests, a set or a table of characters, each one represented by a different value. Encoding is more a process or a function to get the final binary representation of characters. For example, the most common Unicode encoding not char set is UTF-8, which stands for Unicode Transfer Format. It represents each character with the least of bytes possible. All characters from the original ASCII char set are represented by one of UTF's first 128 numbers. Characters after this point start to require a whole new byte. So UTF-8 prefixes each byte with a certain binary sequence that doesn't happen in the first 128. And you guessed right, starting with 1. To let systems understand that they need to aggregate 2 bytes to figure out what character is. It happens again at some point to require a third and a 4th byte. While more involved and slightly less storage efficient than simple char sets, encodes like UTF-8 are smart enough to efficiently store the top most commonly used characters while being capable of storing all the over 1 million characters cataloged by Unicode Consortium. Understanding encoding is crucial when working with text data in PostgreSQL, because choosing the right encoding can affect both storage efficiency and the types of characters you can store. Time is a complex concept in database. Well, time is actually a complex concept in life, isn't it? To explain what databases do when it comes to time representation, think to yourself, what would you do to invent a data type? Should you store date times as free text, like 22nd of March of 2025? Anyone can argue that this has a number of disadvantages. There is no universal consensus of data and time representations. Well, there are some important standards though, and we'll cover them in a follow-up lesson. Most importantly, text representations of points in time are hard to calculate. How does the system know that 10 days from 22nd of March of 2025 is not the 32nd of March of 2025? So why don't we store date and time representations as numbers? However, this brings up a problem probably as big as the entire universe. When is the moment zero? Well, there is a standardization called Unix epoch, which arbitrates the sharp midnight UTC of the 1st of January of 1970 as the moment zero. In the standard order of magnitude is seconds. The famous Unix timestamp is the offset of seconds since the Unix epoch, traditionally allocated in 4-byte or 32-bit integers. Unix epoch-based systems became popular due to efficiency in manipulating dates in probably the vast majority of the systems today, but they are doomed to overflow on the 19th of January of 2038, when the maximum 32-bit integer number will be reached, something around 2 billions. Postgres resolves that by storing timestamps in 8-byte or 64-bit integer numbers, which is so big that allows it to be as precise as storing timestamp in microseconds, and you can rest assured that it won't be exhausted while humanity minimally resembles what we are today.